Hi, everybody. My name is Clayton Miller. I'm a PhD student, doctorate candidate at the ETH Zurich in Zurich. This is my first sort of foray into doing web screencasts and audio recordings of the presentations that I'll be presenting at the conferences that I go to through my research. Hope you enjoy. Today I'm going to talk about a paper that I'm presenting at the SIM-AUD conference, or Simulation and Architecture and Urban Design conference in Washington, D.C. next week. And it is about a process of analysis of sort of screening processes of large measured data sets from an energy information system on campus that we're using to inform the calibration process of an urban scale model. And I wrote this paper with my advisor, Arno Schluter, and I will be presenting this next week in DC. So in this paper I'm going to talk about, or in this presentation, I'm going to talk about the context of the investigation in terms of model calibration, urban scale model calibration, and using large raw data sets from sensor systems or energy information systems on a campus. And I'm going to talk about a lot of the challenges that go into using that data. I'll talk about a forensic process of data analysis and screening, so multiple layers of analysis that are meant to filter knowledge from the data that help an analyst decide how to use that data for calibration, and then an application to a large data set that I collected or downloaded basically from the energy information system on campus. So this effort fits within what's called the UMEM project, Urban Multiscale Modeling Project, where we are taking building information modeling, a building information model using the DPV, or Design Performance Viewer tool that was developed in our lab, and auto-creating Energy Plus building models and a CitySim urban scale model, and then simulating those two engines while coupling them to exchange various information to improve basically the capability of each one of those, and then sort of the end result is visualizing those results and understanding those simulation results. And then this effort is meant to look at comparing those results to the actual measured performance data, the energy data and heating and cooling and electricity data on campus. So to get a sense of what these models are, a lot of you are probably very familiar with Energy Plus. I won't talk too much about that, but CitySim is an urban scale modeling software. This is a screenshot from the designer program, the GUI of CitySim, just showing the campus, the Hungerberg campus at the ETH in Zurich, where the campus has been basically modeled, the geometry has been modeled in the screenshot, and the engine itself is a little more of a simplified simulation engine and focuses a lot on the interactions between the buildings and localized climatic effects and radiation exchange, etc. So we built this model. We also went through this process, and then we basically are looking to sort of calibrate these models with measured data. So the model calibration process. This is a graphic from Paul Rafferty's research and paper where he looks at sort of systematically calibrating models, and there's two basic parts. There's sort of this model input assumptions and investigation, so gathering information from a building to understand how you should initially set up the model, and then sort of calibrating it through an iterative process and sort of modulating those input parameters and then to sort of reconcile simulation versus reality. And so one of the big model inputs are diversity schedules, so occupancy schedules, lighting schedules, miscellaneous loads, etc. Even HVACs have schedules, and these are meant to let the simulation know at any given point during a day or a typical type of day, there's a certain percentage of people or lighting or whatever load it is. And this is a graphic from the Symergy program, GUI for Energy Plus, sort of illustrating all those different types of schedules. And so how can these schedules be developed for the calibration process? How can we create these schedules for simulation calibration as close as possible to what the buildings are actually performing at, essentially. So that's one of the big challenges that I was looking at through extracting looking at this measured data set. So the use of measured data or energy data for these schedule creations, this is a flow chart which is kind of tough to read right now, but I'll kind of explain in general that the first sort of part of the flow, this flow, is to collect reliable, sort of meaningful, measured performance data, electrical data mostly from non-HVAC sources to indicate occupancy and lighting and plug load diversity. And then there's a process that transforms that diversity, that transforms that time series data into diversity profiles for the simulation process. And this was developed by a group of researchers at Texas A&M to develop sort of typical load schedules for input to simulation. And they looked at a lot of different buildings, and they were very careful about selecting the right power meters and installing the right power meters to get good information for these typical load schedules. So how can we apply this process on a real building, a real campus? This is really the challenge that we're looking at. So I'm looking at implementation of this on a real case study. So this is our campus, Hungerburg campus, built mostly in the 60s, 70s, 80s, and there's a lot of new construction now. It's a 315,000 square meter campus, 32 buildings. So it's a very large campus. This is very typical of university campuses. So what does the EMS, or Energy Management System, or EIS, Energy Information System, look like? Well, it's from those 32 buildings. Some have many more sensors than others. But there's a really a diversity amongst what types of performance is being measured in terms of cooling, electricity, heating, but also gas consumption, and then also water consumption. We include that as performance data. So there's quite a few data points, 1,200 plus, I think 1,240 something performance measurement sensors. So that's quite a few to look at initially. So what does that raw data look like? If you look at this sort of image on the far left-hand side, this is a plotting of all those data points, or majority of those data points. You can't really see or read each of those points. This is just meant to show you just the volume of time series data that's in there. And if we zoom in, let's look at the last 4 or 5 data streams. You can kind of see, you can initially see that we have 8 years of data. We extracted this data 1 CSV file at a time, because that's the way the EIS system actually works. And you can already see, the bottom point sort of didn't store data for most of the last 8 years. Some of them have some gaps, some of them have some flat lines. So you can already start to see, okay, how do I take this data? And you can also see the names of the points. And there's a bit of a cryptic, not cryptic, but naming convention, which doesn't give me a lot of information. So some of the observations that there's sort of a pseudo-systematic naming conventions, which allow me to sort of understand where this data is being collected from. But there's large gaps and irregularities. I'm not really sure which electricity meters include HVAC loads or not. And there's a lot of changes over time on this campus that I'm not aware of, and that really digging into all of this information, really understanding this data set, is going to take a really sort of a lot of effort when there's this many data points. So it's interviews, walkthroughs, discussions with the staff to really understand what these data points mean. So in this paper, I'm looking at a more automated way to sort of understand the data without going, how much can I understand from the data without doing a lot of these more labor-intensive processes. So I call this a forensic process of analysis of large past data sets, or an ad hoc analysis. What we do is we take the raw data and we apply various filters. And the first filter is a data quality filter to understand the completeness of the data set. The second filter is a weather sensitivity filter to screen HVAC versus non-HVAC loads. The third is what's called a breakout detection, or time series breakout detection. And this is really meant to understand how consistent the data is over the last 8 years in terms of the phenomena that it's measuring. And breakouts are essentially, in time series, shifts in general characteristics, mean shifts and sort of time series characteristic shifts which would signify with this data that there's a change in use or there's a problem. And I'll discuss that in more detail. And then the last is taking all of these sort of screening steps or metrics and understanding the feasibility of analysis, or just pinpointing which of the streams or buildings to sort of zoom in on, and understanding the next steps in the process. So I'll go through each one of these screening processes in a little more detail. The first one is data quality. So this is very simple. This is just understanding, is the sensor storing anything at all? Are there gaps in the data? Is it sort of meaningful in a way that it could be sort of accurate? And this is really related to flatlining, which is very common for sensor systems, to have the sensor sort of flatline at a certain value. And then getting an idea of anomalous behavior or outliers, not necessarily neglecting those, because those could be important, but just understanding where they exist. So within the screening, each of the timestamps for each of the power meters was assigned a quality metric. The first one's missing data, so it's just no data being stored. One is a flatline data. Two are outliers, which are detected using a seasonal hybrid ESD algorithm, which was developed for time series data which I'll talk a bit about. And then sort of three, which is normal. So anything that's left over. I'm not saying that it's going to be accurate data. It's just there. It exists. It's not sort of an outlier statistically, and it's not flatlined. For outlier detection, I'm using a new library that was implemented in R by Twitter, and they use it for time series data analysis of tweets, apparently. And it's meant to, in a very robust way, and I won't go into a lot of detail about the algorithm, mostly because I'm not an expert in it. I'm using it and I understand it to that level. But it's meant to robustly detect global and local anomalies by decomposing the time series and pulling out the seasonality, and really converting into a stationary time series data set, and then understanding, creating a model and then understanding the differences between the measured data and sort of that simplified model. And like I said, I won't go into a lot of detail. This is just what I used, and it's very interesting, and it seems to be quite robust, but I'm still kind of learning about it. So what that does, when you look at a single data stream example, in this example, the first 10 days are blank data. No data is being stored. Data quality metric 0. Then the data is sort of flatlined for a while. Don't know why. We just know that it's not changing. And is that meaningful? Probably not. It's not very often that you would have a load which is just flatlined like that. And then we have an outlier, which was detected by the algorithm. Not saying that we should remove that, because it does in this case kind of look important. But it's there. We just know it's there. And then quality level 3, which is probably meaningful data. It seems to be modulating. It's not flatlined. It actually exists. So when we apply this setup to, I took a subset, 384 data points, which are electrical meters. And this is a heat map meant to sort of show an overview of all the points with this metric system applied to it. And it's sorted from top to bottom, with bottom being lower quality and higher being the top of it being higher quality. And it's really, this is to visually understand how many data streams that are potentially useful. And it looks like we have quite a few at the top, which are potentially useful data. They have a few outliers, but they're not flatlined, and they do have data. And you can see about 35, 40 of these data streams at the bottom, which haven't really stored anything for the last 8 years. And this is something that's we don't know why. We just know that there's no data there. So we shouldn't spend time trying to understand what those are measuring, because it's just not useful. And if you look at, if we zoom in, the single data stream example, you can kind of see that that's contained within this larger heat map. So the second step we call weather sensitivity screening, and this is meant to tease out or understand or quantify the correlation between the performance meter and outside air conditions, to distinguish between meters that are measuring equipment which is correlated with either heating or cooling, And if it's not, it's weather independent, it's probably due to occupancy, lighting, and other loads which are not weather independent. And this is important when you're building diversity schedules, especially for occupancy and lighting and things like that. You want to avoid using data points which are weather dependent in measuring HVAC loads. So in order to do this, we use a sort of a common practice, the Spearman rank order correlation coefficient, where we're looking at each data stream and how it correlates to outside air dry bulb temperature. And so this coefficient is calculated across a time span where the data stream and weather are reordered based on ranking, lowest to highest, and then those rankings are then using this equation converted to a coefficient, which is meant to just show that correlation coefficient or correlation between the streams. So here's 3 examples. The top one is and it's the coefficient is anywhere between -1 and +1. +1 is highly positively correlated. -1 is highly negatively correlated. 0 is not correlated at all. And therefore, here we have 3 examples. The first one's cooling sensitive. 0.939, very highly correlated. This is probably strictly a cooling meter. The second one is completely weather insensitive. You can see across the outdoor air conditions, there's no change correlating. And then a weather heating sensitive, so negatively correlated. So we create another one of these heat maps to show over the last 8 years each of the data streams and how they're correlated with weather. And I performed the coefficient calculation for half years or seasons, so to understand seasonality and see if it sort of changed. It doesn't change a lot for most of these, but you can see that there's 50 or 60 some electricity meters which are sort of highly heating correlated. There's a few that are highly cooling correlated, and then you have a lot that are sort of somewhere in between, and these are the ones that we would want to focus on in terms of investigating whether they're lighting or plug loads or things like that. The last step is called breakout detection, and this is a little more of an advanced concept focused on time series data analysis, and it's meant to look at each data stream and then understand its tendency to shift from one general performance state to another with some sort of transition period in between. And these are, I'm looking at a long-term tendency to shift, and I'll show you what I mean. So I also used another Twitter library that was implemented in R, which they use within time series analysis of tweets once again. And like I said, it's looking at this sort of mean shift between of time series data as it shifts between one performance sort of state to another. So there's a mean shift, and there's also another type of breakout called ramp up. So, and what does this mean for buildings? Well, here's an example of a power meter, this is about, like 7 or 8 years worth of data from a power meter. And you can see the first like 3 or 4 years or 5 years, the characteristic of this power meter and whatever it's measuring is quite consistent. And the differences in color, the changes in color, are where the algorithm detected a breakout or a change in performance. And you can see it's not perfect. The difference between the green and the yellow, if I were visually looking at this, it would be over to the right a little bit where it shifts down. But you can see that it's generally accurate in understanding the number of sort of performance shifts. And these shifts, I don't know what the issue is, why this power meter has shifted so much. Maybe it's equipment, maybe it's a server, something. But really, you can see that there's a strong difference in whatever phenomena that it's over time that it's actually looking at. And this helps us understand how consistent the data is over time in order to understand. So this is another heat map. It's sorted from top to bottom, with the bottom being the least number of breakouts detected over 8 years, and the top being the highest number. And I set the threshold such that it can only detect a maximum of 14 breakouts over this 8-year period. It's because I'm really looking for just macro level changes in performance or in behavior. And so this is meant to sort of show the range of breakout characteristics of this data set. And ideally, if I'm going to calibrate a model, I want to use probably a little more consistent of data streams, or just understand what that breakout tendency is for the data. So this is after you've performed those 3 screening processes or metrics. The last thing to do is to compare or to sort of cluster these data streams according to their data streams that are similar in tendency. So this is a hierarchical clustering visualization, which is showing the 3 steps, 3 metrics, and then you can kind of see that they sort of form, or I've assigned them into 4 different regions of data point types, region 1, 2, 3, and 4. And region 1 is lower quality data, just maybe not as complete. It's a lot of these data points that just don't have as much data stored. And I'm just going to look at those last. They have quite a low number of breakouts, but they just have a low amount of data, so that makes sense. Region 2 are data points which have a high sort of number of breakouts, are seemingly kind of weather sensitive. These are probably HVAC loads, heating and cooling loads, and that's fine. I know that. Maybe if I'm looking for lighting and plug load occupancy schedules, I'm going to look somewhere else. Region 3, moderate number of breakouts and quality, seemingly weather insensitive. So these are really good candidates to sort of zoom in on and understand whether these are lighting or plug loads or something that can be used for diversity schedules for occupancy. Region 4 has sort of varying quality, but has some really good quality. Low number of breakouts. You can see how the red there's is very consistent, and they're generally weather insensitive data points. So these are really great candidates to zoom in on and understand whether they can be converted into diversity schedules. So the last thing, and I haven't done this for all of the points yet in this process, but I would transform these region 4 into candidates into typical daily profiles. And I use the day filter process, which I published a paper in Automation and Construction, which focuses on this process of filtering patterns from univariate data according to daily profiles and dividing those into normal and abnormal, and then clustering those into typical profiles. And I did that in this case to kind of illustrate one of the data points converted using day filter, and it came up with 5 different types of performance, sort of 2 weekend type schedules and 3 weekday type schedules, which seem to have sort of a standard offset. And this is a really sort of normal type of schedule, occupancy schedule, and the algorithm does this in an unsupervised way to tease out the different types of time series or daily performance. So this really can then be potentially investigated a little bit more and then normalized according to peak versus internal profile, and then assigned to the days within the simulation. And this is a process that's ongoing. I don't have data quite yet on the accuracy or the calibration process at this point, but I can tell you right now that I was able to essentially apply all these filters, apply the data filter process to all these 1,200 data points in about 30 minutes on my computer, 30 minutes of processing time, and that results in this insight or this information, which allows me to then go and discuss with the operations team and really pinpoint maybe where I need to do more investigation or less investigation to understand these diversity profiles. So to let you know about my philosophy of research, this whole process is really meant to have an impact in real practitioner or analyst workflows. And so I provide all of these 3 steps, and this whole process is available in IPython notebooks, a web-based format, online. The data set is available, and the actual process to create all of these graphics are out there, and I can send them to you, but also to let you know that they're also on my research website, datadrivenbuilding.org, where I have many other types of analyses, the day filter process, etc., which is being disseminated. And you can download these notebooks, you can implement them on your own computer, and then you can maybe use them as templates or inspiration for your own data sets, essentially, which is just something that I'm committed to doing throughout my research is in order to make the biggest impact. So this is all I have for today. This is my last slide. If you have any questions, be sure to email me, but also subscribe to Data Driven Buildings and subscribe to this YouTube channel and for more updates on my research. Thank you.